It's not coffee. So I'm going to go ahead and express a controversial opinion. I like the American version of The Office better than the British version. This isn't just because I'm American or because I don't get it, but rather because I think the American version has better characters that are more fleshed out, the series is longer, and frankly, I think it has funnier moments. In short, I like the American version of The Office because they took something that was already really great and made it better by expanding on it. We are going to talk today about a very similar concept, phasors. What phasors do is allow us to expand on DC circuits and use all the knowledge we've already gained to extend into AC or alternating current circuits. A phasor is just a representation of a sinusoidal signal. Phasors are complex numbers, so they can be represented either in rectangular form or in polar form. Let's suppose we have a signal v of t, which is equal to a cosine omega t plus phi. Then the phasor representation, which is either v vector or v tilde, is equal to a angle phi. Similarly, if instead of a cosine function we use a sine function, for example, I of t equals to b sine of omega t plus theta, then the phasor representation is just going to be b angle theta minus 90. So for the sine function, we just add minus 90 to the angle. These representations are going to work great as long as I have the same frequency for all the sources in my circuit. We can also introduce the idea of impedance. Impedance is the AC version of resistance. It allows us to generalize Ohm's law to AC. Ohm's law, generalized to AC, is V equals I Z, where Z is impedance. For a resistor, the impedance Z is equal to R. For a capacitor, the impedance Z is equal to 1 divided by J omega C. And for an inductor, the impedance is going to be J omega L. Let's go ahead and apply this to an example. In this example, I'm given a sinusoidal current I of t is equal to 12 cosine of 500t plus 45 degrees amps, applied to a 10 millifarad inductor. I want to find the voltage in the inductor. First, we will find the phasor equivalent of each part, the signal and the impedance. Let's start with the current. The impedance transform of I of t is I vector, which is 12 angle 45 degrees. Next, let's find the impedance of the inductor. We know that the impedance should be J omega L, so we calculate this and we get J5 ohms. Next, we use the generalized form of Ohm's law, which says that V equals IZ, to see that our desired phasor voltage is equal to 12 angle 45 multiplied by J5. J is just angle 90, thanks to complex number rules, and so the second term becomes 5 angle 90. Multiplying these together, we get 60 angle 135 degrees volts. However, we are not done. We have to convert this back to time domain, which is simply V of t is equal to 60 cosine of 500t plus 135 degrees volts. So, what's great about this is that it's just an extension of DC. In fact, in the coming videos, what you'll see is that all of the rules we learned in DC apply to AC. We're just doing math with complex numbers. What we're doing is taking something good that we understand reasonably well, and we're making it better by generalizing and expanding to AC circuits, which is why the US version of The Office is better than the UK version. Thanks for watching this video. If you think I've earned it, I would love it if you would subscribe. You can find me on Twitter or Instagram at BD McPheron. This is Dr. McPheron. Set phasors to stun.